Hi, my name is Pramod of the CoinOp Collection, and today I'm going to talk about how to use documented and physical sources for your FPGA core. So normally when we start out programming the core, there's a few pieces of information that we need in order to kind of put together things and do research and all that sort of thing. There's a lot of sources of information for putting together an FPGA core. And so what this video is about is I'm going to go through kind of some of my process, but also different sort of scenarios where I've used different sources of information to solve problems that come up during the FPGA development process. Now, most of the time, what I can do is I'll run through a basic information check to see what sources I have, whether that be manuals or current known working emulator sources, physical pictures of the board, the actual board itself, tracing. There's all these sorts of information that I use to put together different cores and solve different types of problems. But depending on what type of problem you're trying to solve, or uh, rather what the architecture of the board is and how the architecture is laid out, you might find yourself in different situations where you're using different pieces of information to solve different types of problems that you might have or that you may encounter. Okay, so generally to start with, I take a lot of pictures of the board most of the time. I have a lot of experience now, so basically I've been doing this reverse engineering boards. I've been probably doing it over 20 years. So I have a lot of experience with late to early 90s boards. Usually I don't touch stuff from the 80s, and I don't actually have a lot of 80s boards in my collection, but I just kind of focus on 16 and 32-bit systems. That's primarily, the period that I focus on is those platforms. And so most of the time, if I have a board in my collection, actually most of the time I'm working with a board that I have in my collection. And I will a lot of the times take very detailed pictures of them. So I'm going to show you an example here from Batrider where I've taken a lot of pictures. So I'm going to show you this. This is a collection of photos that I have. So I take really detailed photos of the board, like pretty much every aspect of it, just to kind of see that the component labels are marked, and that the components are visible, any markings on them are visible, any local traces that they may go through, like these are local traces that they go to. So I can see where the customs are and where they connect to, so I can kind of discern what they might be doing or infer where they might be going to. So I take lots of detailed pictures of the board at different angles, different lighting, just so I can see things clearly. Now, um, what I tend to do after that is I create a merged picture. So I'm going to show you the merged picture. This merged picture actually has the front and the back aligned properly, and so you can see the through holes, right? So you can see the back traces on the board, because often at times when we do a routing on the PCB, traces will start in the front and then they will end up in the back and then they'll go somewhere else, right? So I usually do this merged picture. It takes a lot of work to get it aligned, and a little bit of Photoshop to get everything squared away in terms of the lighting and stuff. But this actually helps a lot in terms of understanding, because you see, like, even these sorts of things, right? You can see where the traces go and where they go to. Now, I don't copy the schematic exactly. What I try to use this step for, what I try to use the physical sources for, um, of the board, is to understand what is going on. I want to be able to understand, first of all, what components are on the board. And the markings on the chips tell me what components there are that I have to work with. So I will look up data sheets. And I think I've shown that in the previous video, where I start looking up component numbers, start looking up data sheets, seeing if there's existing FPGA IP that I can use, or any sort of hint as to what that might be doing. Right. In the case of the Rising platform, there's a lot of customs, right? So you see you have AFBK CT2, you have the EDEC chip, which is an address decoder, and then you have this. This is the DMA controller, I think. Um, and then this is the 68K. Um, so I'm sorry, this is a VRAM controller, text VRAM controller. Um, and so like I'll have these different labels on the chips that I look up, and I can see what they do. And sometimes what I do is I have different sort of probing clips that I use. So like for example, like this chip is a chip that I've traced before. And so what I'll do is I have a clip that goes on this where it makes the probe pins bigger, so I can actually attach uh, signal probes, logical probes, to probe what the signal looks like, so I can get the data output from this and see what it's potentially doing. Okay, so I do attach probing clips to each of them, which I find I need more information on. I don't do this with every single possible chip. That's not a good strategy. What you want to do is you want to understand the board to a point where you understand what role each of the components play. You want to inspect how much RAM you have. That determines how much memory the board has to play with and how that might play a role in the game. You also want to understand what role the actual chips play because you want to be able to emulate their functionality. And you also want to understand where the ROMs connect to because you want to understand how much bandwidth you have to play with in terms of this data going to different places like RAM or some other custom chip that does banking, loads up graphics. You want to work out all of that and start to work all that out, on the physical source of the board. So that's what I use the physical board for. I take lots of pictures. I want to be able to, at the end of the day, take a look at this, understand what each chip is doing, what role does it play. In the case of Rising, there's a lot of custom chips that are involved. And so each of these chips I have traced out, I've captured data from in order to understand what they're doing. I haven't decapped any of these. I normally do not work with decapped sources or tracings of that sort. We have another guy in the group who does that. I have not really gotten into that. I just don't find it helpful for my workflow. But what I like to do is I like to look at data because in real life I work in data science, right? So I like to take a look at data. I like to take a look at sheets of data, especially time series data. I want to see what data is outputted by what chip, what does it mean, decode the data. I want to figure out what role it plays in. So I really am a dig into the data sheets type of guy. I do not use waveforms most of the time. I use waveforms for some types of problems, but most of the time I don't use waveforms. I prefer to capture data from different chips. If necessary, I look at the data and I try to figure out what it means and what role does it play. Okay, so that's how I use the physical sources that are available to me. Now, the next thing I try to do in terms of enhancing my understanding of the board and the platform itself is I like to go into manuals if some of them exist. So um, this is a manual for the TMS 34010 processor by Texas Instruments, and I've implemented the entire CPU. And this is what's used in my Midway core. But you can see this is a pretty lengthy manual. This is like something like 600 pages. And so this manual actually provides detailed information on every single possible aspect of the CPU. And it's highly detailed. It has timing diagrams, it has logical diagrams, it has all the sorts of things, architectural diagrams. So all these sorts of things I go through the 600 pages and I start implementing them. No, I don't start from page one and just start working my way down. But what I try to do is, first of all, I take a look at the block diagram. The block diagram appears like in the beginning somewhere. And what I try to do is I take a look at the pinout first of all, see how the pinout helps because the pinout tells you how the CPU or that component, this is not only for CPU, it's for different component chips, how the chip interfaces with the outside world. Because a lot of the time, the question is not what does a specific chip do, but rather how does that chip communicate and work with other chips on the board. Okay, how does it interface to memory, if any memory is connected? How does it send commands to other components on the board? How does it access the address bus? What's the width of that? Because the width of the address bus determines what your bandwidth is, right? And how it might have been doing that and what's the speed it might have done, right? So all these kinds of things are very important for discerning, again, enhancing your understanding. Here's your block diagram, the architectural overview. Yeah, I start with the block diagram. I literally create these modules, in this case, in Verilog, and then I start looking up each one of these, filling in the gaps. In the case of this CPU, this is a very large CPU. It's got 128 instructions. That's combined both graphics and regular computational instructions, memory instructions, and the sort. And so I needed to create a microcode engine for this CPU because I built it in by using regular logical elements at first, and it was too large to fit. So I created a microcode engine to do this. So there's also sorts of design aspects you have to go through, when you take a look at different chips and use the manual and data sheets to discern that. Second type of source that I use to enhance my understanding are schematics. This is the service manual for NARC. And you can see here, it has some elements here which are like introductory elements and descriptions of different sorts of aspects of the settings, but also what it has here is schematics, right, that I can use. I can use the schematics, um, and I think I've shown this in a different video where I've used a schematic and actually implemented that in Verilog and showed you step by step how I might do that, right, by looking at the schematic, what role it plays, what the importance of it is. But in my first initial stages of research, what I try to do is I try to take a look at the schematic again to enhance my high level understanding of the platform. Right. My goal in the first is to take pictures of the board, find out what the components are. What do these components do? How do they communicate with each other? Now I'm taking a look at the schematic. Okay, all of a sudden it's starting to make more sense. Are there any block diagrams? Is there a high level schematic? How do these components fit on the bus? How do they communicate with each other? So I'm trying to fill in these sorts of gaps about the platform. And so when I do that, I tend to take a look at schematics. Most of the time, schematics are not available. I don't really build schematics. I mean, I can do a partial schematic just to enhance my understanding, like on a piece of paper or in KiCad, if what I'm working with is extensive. But normally, I do not do that. I just simply try to take in the information, process it internally, and try to understand what is going on, how this might have been accomplished. What was the role of this? What was the designer thinking when they created this platform? What was their intent? What did they want to make run on it? Those are the questions that I want to answer in my initial phases. Then we can get down into the low level detail of, oh, what does this do exactly? Like, what is the algorithm or something? But most of the time at the start, I'm not asking those questions. I'm not asking what the algorithm is. What I'm asking is, what does it do? How does it function? How does it communicate to other components on the board? What's the technical specification? How much memory does it need to operate? Like, these basic sorts of questions are things that I cover in my initial stages. And then after I cover my initial stages, I'll have a high level roadmap of what I need to build. If there's existing IP to cover different things I want to do, or I need to build IP, then I will, go through the motions of, oh, what is this specific algorithm for this thing? Or how do I structure this in terms of an architecture? So I'm trying to answer those questions at the start. And when we get down into low levels of detail, manuals like this help. So this provides some low level of detail into the ZUnit platform. I found this manual online. It's a pretty good manual. It has some good information in it that I've used to solve different sorts of problems. Like how do some of the customs work, right? How does the DMA custom work in this platform? Because the DMA does all the graphics processing, right? The GPU functions of the TMS are not really used except for the post screen where it draws the PCB and it starts, lighting up components that either fail or pass. That's the only part the GPU is used in. The rest of the stuff is all DMA. It's just a custom chip. So it helps me understand the custom chip. It also helps me understand the bandwidth that's playing with on the bus, right? So this system obviously needs a high level of bandwidth. So I want to understand how they achieved that. What did they do? Did they do bit replication? Did they do like literal like huge bus width, like 32-bit, 64-bit bus width? Did they use different types of memory, like an SRAM chip or a high-level SRAM chip? Like I want to understand how they achieved the bandwidth, because those are the data rates that we need to achieve in the actual FPGA core. Um, the FPGA core, though, is a translation of analog to digital logic, right? So you're not going to be able to copy this exactly. You can get the high level architecture in there, but ultimately, due to the way the FPGA dev board is designed, you're not going to obviously be implementing all of this exactly as you see it. You're going to try to take what's here, and then try to replicate it using digital logic, and using different sorts of components to achieve like memory rates or different sorts of techniques that you might use using FPGA resources to replicate. Okay. Now, so in the absence of these types of detailed manuals not being available, or to supplement them, I tend to use MAME. Okay, and I think you've heard a lot about people using MAME to program FPGA cores. You've heard about MAME ports. I don't know what that means, but I know you've heard about MAME ports. Um, and Generally speaking, using MAME, I think, should be the base of what we do. And I'm going to tell you why in a minute. So I'm going to go to JT Course here, which is Jose's repository. Now, like I said, MAME is a very important source of documentation for us. Now, to the outside world, to the normal person out there, MAME is a software that plays retro games and emulates ROMs and all these other systems, right? But the reality is that MAME is not that. It happens to be a working emulator that can play games. It has inputs that you can mess around with. You can play games in MAME, but the actual purpose of it is documentation. So I'm going to open up cores directory here in Jose's repository, right? And for example, go to aliens. Now, if you take a look at the doc directory in any one of these cores, you'll notice that yes, it includes dumps if they exist, like JEDEC files. It includes schematics, which most of the time he builds that in house, right? He builds schematics in house. He has people that do that. But also you'll notice CPP files. These CPP files obviously come from MAME, right? They're different sources in MAME, which are used to as documentation. Now, in the past, right before FPGA technology took off, right? People used to do what we're doing now, but in software, right? Because FPGAs, they've existed for a long time, but they weren't really mainstream. They were very expensive, and there were different types, like the types of FPGAs that were available back when MAME first started. Are certainly different than they are today. Today, it's a mature technology, right? Back then, it was partially analog. There are partial analog FPGAs, and there are just different types of FPGAs that existed back then. But people who contributed to MAME actually went through the same exact steps that I'm going through right now and that we are going through today. Okay, in that they acquired a board, they would inspect the physical components, they would take a look at manuals, right? Things to enhance their understanding, and then what they would do is they would program a software version of a working emulator to emulate that board, right? So we're not doing anything wildly different, except the technology that we're using to emulate things is an FPGA, right? And that has advantages and disadvantages as well compared to software emulation. I think they're comparable though. So if you take a look at software emulation, I think that a big strength is memory. Often at times we run into memory constraints in FPGA, and I think you've heard me talk about this very often in running into memory constraints, because I tend to work on cores that require a lot of bandwidth in SDRAM, ROMs, or memory storage. So I tend to run into these types of problems for some of my stuff because I focus on the 90s period boards. So in a software emulator, This is actually a big advantage because you have an operating system overhead. You have an efficient way and fast, extremely fast RAM in your computer right now, or whatever sort of architecture you're working with. And so you can get that memory, you can put things into it, take things out without really worrying too much about constraints. Plus, your CPU access is basically governed by the operating system, right? So you can run it as fast or slow as you want to. I mean, depending on how powerful your computer and CPU is, the emulator might work, differently. But in the FPGA world, um, that experience will be the same across all the units that have that FPGA in it. Now, there may be cases where you have different dev boards and you're porting it to different platforms and all that stuff. But generally speaking, as long as the FPGA builds, and it's a comparable FPGA with similar logical elements, similar cells, and all that stuff, it should technically work the same. But the memory that's attached to any of these dev boards is different, right? So it's harder to work with, I would say, and that's one of the cons of FPGA is external memory. I think it's not so easy to do that. And if you're writing code in C or C++, that's extremely easy to do. You can just say, oh yeah, memcopy, boom. It's done like in microseconds, right? Like that's not even something that's a concern, right? That's a heavy concern if I'm doing an FPGA core. So there's advantages and disadvantages to both. And I think one of the biggest advantages in FPGA is a timing, right? Because there's more precise clocks. In the CPU world, everybody has a different speed processor. The emulator might not work the same across different sorts of processors because they all have different speeds and ways to govern its clock rate. There's a lot of complexities in terms of achieving the right timing in a software emulator compared to an FPGA. So there are advantages and disadvantages, but I think everybody is in a place right now where we tend to use no, we will use MAME as a base because people back then, like I said, although they were using different technology, they went through the same steps. They got the board, they traced the board. I mean, if tools were available, they physically inspected the board. They figured out what the components do. They figure out by reverse engineering the program ROM and or other components on the board what they do. They dumped out chips. They decapped chips sometimes. And so like all these sorts of things they have done. And so like all that information appears in MAME because you can see like at the beginning of the MAME files, right? You can see that it does give you very detailed information before, I mean, presenting any code. It gives you a lot of information on what some background on the board or the thing that it's trying to implement. So a lot of the documentation we have today exists in MAME, and so that's why you see it prominently displayed in every doc directory in the JT cores because it's a very critical piece of documentation that we use. Okay, so what other things does MAME tell us? So let me take a look at this for a second. So let's see. So we're going to go to source, and this is the MAME repo that I'm showing you right now. Let's take a look at, for example, data east, right? I can take a look at any one of these. Boogie wings. This may not be a good example. Let's see here. I want to show you one that has some semblance of schematics into them. Okay, so Deco 32. These are some of my favorite games. Definitely got Captain America up there. It's my favorite game on this platform. And you can see that um, there's a lot of information here. And you see they even went through and drew the board in ASCII. So you see like all this and all the components, component parts, the customs, what they do. This is Night Slashers. So you see like they've gone through extensive detail. This was back then. This is not something recent. This was done way long ago, before any of us were even online doing FPGA cores, right? This is something that they've documented, and we take a look at these, and you see, look, it even has like some of the components, the clock rates that they operate at, the packages. Like, there's a lot of detailed information in addition to the board layout and different information in here in the driver. So that's something we take a look at. What else does MAME do for you? One very critical thing that MAME gives us is the memory map. The memory map is extremely critical to any emulation working, because that shows how the CPUs communicate on the bus to other devices. Without this memory map, we have no idea how the CPU actually communicates. Now, a lot of the time, uh, these sorts of things, address generation and memory mapping, are usually done out of a custom chip or a GAL. Usually, I mean, for the boards that I deal with, I mean, I don't know back then in the 80s, they probably did it, using regular logical components, right, as opposed to custom chips that do the thing. But the boards that I deal with, like 99% of the time, yeah, probably like 96, 97% of the time, the uh, the actual game will use a custom chip to determine what these are. So where did they get this from? So if there's a custom chip involved, where do they get this? How do they do this? Well, um, in addition to being a very good source of documentation, MAME also has an assembly debugger, right? So the assembly debugger allows you to load up a program ROM, and you can actually see what the assembly looks like and what addresses it's doing. And like, you basically go through and step through the code, and you can figure out, from a CPU perspective, what addresses they're requesting. So for example, in this case, if the CPU requests something on address 130, 130, well, I don't know if you can see this, but just make this a little bigger. Whoa, that may be too big. Um, yeah. So if the CPU goes through 130, right, on the bus, um, and if it falls within this range of 130 to 131 or 132, that means it's trying to write to RAM, palette RAM, right? So that's your palette RAM ranges, and from this you can discern that the palette RAM is 2,000 hex in length, right? So 2,000 addresses that it has, and this is write 32, so it's probably 32-bit addressing. Okay, so that's that, and then there's different functions for different addresses that it tries to output on the bus, and they map to different devices and different things that the CPU tries to do to perform its functions. So this is one very critical component that MAME gives us, is this information. Now, I think though, beyond that, there's a lot of reverse engineering information that exists in MAME, and if you take a look at the V files in particular, um, you'll notice that there are different reverse engineering informations about the graphics. Um, see, about the graphics and about different components of the graphics that that the game uses, right, and how it functions. So this becomes a very critical component uh, in doing the graphics engine for the game, right? And I follow this pretty closely, I would say, because um, no matter how much you trace out a board, like, determining a graphics algorithm, or the algorithms that are used to draw pixels to the screen or render sprites or that sort of thing, you can't really determine that very well by tracing a chip. That's not the most efficient way to research that problem. Um, Primarily, what we use to research this problem is, I mean, if we're starting from complete scratch, like there's literally no information out there, no working emulators, what we usually do is we load it in the assembly debugger, and we find the routine that draws stuff. And we know it draws stuff because we know what those types of routines look like, and then we step through the code and figure out what it's trying to do. What are the RAM formats? How does it draw? Where is the sprite queue? Where is the object queue or background queue? Right? There's some sort of queue If it's hardware sprites, there's usually some sort of queue that happens that it goes through, and those are used to generate addresses to different graphics tiles in the ROM. You pull those, you decode them, put them somewhere. Like we want to get through all those sorts of information, and it is in the it's all in the program ROM. It's all in the assembly code for the game. Okay, and this explains it pretty well. I mean, there are various drivers that are varying in detail. But I mean, just taking a look at the code, you can see how to kind of implement this. It's not something that you should trace on the board. It's something that you should use the experience of past engineers who have dug into these types of problems and follow what they're doing. So normally I follow graphics implementation routines pretty closely, with some exceptions. Okay, and I'll show you what one example of an exception. So I'm gonna go to I'm gonna go to Technos, which is what I implemented recently, right? I will go to this, for example. Okay, so you see this. This is the hardware for Double Dragon 3, right? So I follow this, and see here, this is the RAM format that I'm talking about. So obviously I know what the RAM format is, because I know it was reverse engineered, and I know it's in this file. I know it's documented here. So I follow that. I know what that is. Um, but if you take a look um, at this, the interesting part about this game is that, no, this maybe not be a good example. Hold on, let's see. Which part of what I was looking for? Um, you see, the interesting part about these boards for Technos is that the Y actually is offset by 8. So it goes from 8 to 248, right? So it's 320 by 240, right? And then the vertical display height is 240, yes, but the line counter starts at 0 and goes all the way to something like 272 or something like that. But 240 of those lines are active lines, okay? And it starts from 8 and it goes to 248. But I think they cannot do that with their engine in MAME. So what they do is, when they do the calculations for where the graphics goes, so you can see here that they're calculating the X and Y positions and all that stuff. What they do is they add an offset of 8 to everything, all these calculations. And so if you were copying this from MAME, it really wouldn't work, right? Because that's not how the line counters work, right? That's not even how graphics are drawn, even in a lot of the boards of the past. What MAME does is, it draws things on a tile by tile basis, right? So there's an engine, there's a tile map engine, and it draws things on a tile by tile basis. So you can see here, they have a pointer to the screen memory. They have the bitmap they want to draw, whether it's clipped or not, and they have a function called draw, which does all that stuff. Draw is a centralized function that does all the stuff, and it draws pixels to some memory. That buffer is flushed to the screen. You see the screen, it goes to the next frame and the next frame and so on, right? But you can see here that there's a lot of heavy calculations here in terms of how the RAM is used. This is sprite RAM, right? And how that's used. And so, like, their calculations are going to be slightly different because they are drawing things differently. Now, how I draw things, right, which is how the boards usually do it, is through line buffers. So we draw things line by line. So you can't draw a whole tile or a whole frame. I mean, I guess you can draw a whole frame at once, but that's not how the boards work usually. Usually the boards work by drawing line by line. So you're in the horizontal blanking area and you're buffering 1 or 2 lines ahead, sometimes 3 or 4 lines ahead, right? And you're drawing to a line buffer, and then the line buffer gets flushed to the screen when the line counters go, and it's in the active area, and it puts pixels on the screen, right? That's normally the procedure for an FPGA core, which is not all that dissimilar from how it was doing it on the real boards. Okay, some boards have a full frame buffer though. Not very many, because you can imagine that there's a lot of memory required for that, right? But the point that I want to get across is if you were copying MAME directly, um, that wouldn't work, right? Because the graphics are just drawn differently. That's not how the original board behaved. And actually, if you do it this way, you're going to face memory constraints potentially. And you may not even have enough memory actually to do it, depending on what's the color format and how much bits per color that you have to work with, and what's the pixel clock, right? You may not even have enough bandwidth to do it. So we use MAME as a base. We do take a look and follow this closely, but we don't copy it necessarily 100%. We take a look at it, try to understand what's going on, create our own calculations if necessary, and then do the implementation in a line buffer way. Okay, that's concerning graphics specifically. Okay, so that's MAME. So MAME is used for specific algorithms, specific address bus routines, different sorts of information about the board from a low-level reverse engineering perspective. What's the RAM formats of the graphics? How to decode things? There's lots of different reverse engineering information in MAME, which we normally don't. I mean, it might take us months sometimes to get all that information from scratch if there was no source for it. So that's why MAME is a very good documentation source for people who are writing FPGA cores. Okay, but we don't copy this for sure. It wouldn't work. It just would not work. The engines are completely different. What MAME does, how it manages memory, how it manages the graphics. Uh, there's many layers to it, obviously, and it just would not work. Period. Okay, so there's no concept of a MAME port or anything like that. Well, I guess what people are talking about doing is taking a look at MAME and discerning information about a platform and then implementing it by hand. There's no concept of a MAME port. Stop talking about that. It just doesn't make any sense. Okay, there's multiple different concepts going on. MAME is a totally different world that has nothing to do with FPGA cores. Okay. There's no magical process that ports something from one to the other. Even if you were an expert and you were just looking at this, it would be very difficult, if not impossible in some cases. So th- that's that's basically what I'm telling you. Okay. So in the absence, okay. So we use MAME for that sort of thing. We use the manuals. The next sort of thing is not always available. Okay, it's not always available, but it's sometimes available. And in this case, it was available to me. Is I use the source code for the game. Okay, and this is the NARC source code. There's a lot of different source code for the Williams platforms online for free, and you can take a look at them. But this was actually helpful, and I'll tell you what problems it did solve for me. So I am in somewhat of an expert in TMS assembly because I implemented the whole CPU. Not only that, but I implemented all the instructions multiple times because I found there were bugs and I had to keep going back and do it over again. Then I found out that I had to do it in microcode, so I did that too. So I must have implemented all the instructions and everything for the CPU about 20 times now, over the course of the year. So I know it pretty well. And so what I use this code for is I'll show you right now if I can find it. I used it actually to understand the DMA chip more because I wanted to figure out because a lot of this platform is software driven, and so that was very interesting at the time. Okay, at the time you had boards that had like you had hardware sprites, right? So you'd have a custom chip that did sprites, for example, right? Um, what was interesting about this is the CPU was really the center of the design for this platform, and all the stuff that they did was software configuration. So normal things that you might have, like for example, video timings. Video timings were all done programmatically. So there are literally video timings in the code, in the assembly code, that it pushes to registers on the TMS, and then the TMS uses that to generate the video signal or the video timing signal rather, and then that can be used to generate your line counters and all that stuff, and then ultimately draw graphics on the screen. But what's interesting is this is pretty software controlled. There's no hardware sprites in this platform. It's all software, blitter based routines. And so I wanted to figure out what was going on because, and this is where the source becomes very important, is because um, since there are no hardware sprites, there's no RAM format, obviously, right? It uses its own scratch RAM to do its own thing because it's all done out of the CPU, right? And so um, you want to get into the source code to tell you how the thing is actually drawing objects. There are software sprites, I would say. There are software objects, software sprites, and software backgrounds. So all that stuff is in the program ROM. And aside from looking at assembly in MAME, which you can certainly do, you can look at the disassembled code. What better than the actual original programmers' comments and routines and how they structured things? What better than that to look at, right? And there's some interesting comments, in this file, right, of what the routines are doing. Um, and I use this very heavily um, to understand the DMA chip, how they worked with the DMA chip, and how they set up things. So look at this. It's all commented, and it's the original programmer that did the game, right? The original programmers who did it, Eugene Jarvis and George Pietro and all those guys. So I followed this very heavily, and so I use this as a primary source of information, one of the primary sources of information for me. Okay. Also, I want to leave you with a note that what you see in MAME is not the be all end all because it works differently than an FPGA core. An FPGA core, you need more information, often at times, to get it even working, right? So in the case of Technos, I think I mentioned this in some posts, is that there is a very specific interrupt that operates at a certain rate for input, right? So there's an input polling interrupt, it's a constant signal that operates at some frequency, right? And that's obviously not implemented here. It's not. I mean, it doesn't even appear anywhere. Not even as a comment. It doesn't even appear as a comment in the code. So I actually had to break out the board. I had to hook up my logic analyzer to it. I had to trace. I had to hook up uh, traces. I had to hook up leads to the 68K IPL pins, see what the rate is, and then create a clock enable for that rate, hook it up to the 68K in my FPGA core in order to make things work. Okay, so you might find yourself doing that. Um, Another example that I can think of is Sorcerer Striker. In Sorcerer Striker, the audio would just not work for me. There, I had a lot of complaints where the audio was out of sync. It was like skipping. It was too fast. It was too slow. And so what happened was A-Track had the board actually, and he managed to capture some information for me, and also capture some of the information on some of the traces or where pins and where they're connected to, and I was able to figure out what was going on and why my sound wasn't working properly because of that. But again, that information not existent in MAME, and it doesn't need it actually. The way that it's working, the way that the components are hooked up, and the way they're running, it's not critical. It's not critical to the emulation of the platform in MAME anyway, based on the engine that it has. So there are times when that happens, and so you have these different sorts of problems. So what you want to do when you're programming FPGA core is take a look at the problems that you have in front of you and try to figure out, where can I get this source of information from? What do I need to solve this problem? So you want to always do a problems and solutions approach, like when you're programming FPGA cores. You want to implement like the skeleton of the platform first. Then you want to go through and see what sort of problems you're facing. Oh, it's the graphics are not drawn correctly. Where can I get that information? Oh, MAME has the graphics routines. Let me double check that. Let me check source code if source code exists. Let me check technical documentation. Like you want to figure out the most appropriate source for the information that you're seeking and try to solve that problem. And you can only go one problem at a time. So that's basically what I do. I mean, I take a look at the different source of information, which I showed you in this video. I go through, I start programming the platform, the skeleton for the platform. Then I start digging into each of the components. How does video get drawn? How does sound work? How does the CPU communicate to other things? Like I start implementing all these low levels of detail, and then eventually, after some time, I end up with a pretty much complete skeleton that runs the program ROM and does stuff. And then I need to fill in gaps. Okay, the graphics are not quite right. Let me dig into that. Let me create a sim bench where I just isolate graphics rendering. Let me take some dumps out of an emulator, memory dumps, and let me try to see if I can draw those graphics properly. Keep iterating through it until it's pixel perfect, right? So I try to do those types of things, and I try to figure out what's the most efficient way to solve a problem. And generally, you want to do a problems and solutions approach for these things. So I hope this video is very helpful for you. So I hope this helps you on your journey of learning and developing FPGA cores and your education in general into this world. Thank you.